Example number 2. So we're going to let S be the same surface. Let S be the same surface as before. In other words, the upside down paraboloid be the same surface, which is z equals 4 minus x squared minus y squared, z greater than or equal to 0. And this time we will let our vector field f, we will let it equal to xy, yz, and xz. Okay, so we have our parameterization, which is always what we want to start off with. Xy is x and y, and of course the function itself, 4 minus x squared minus y squared. Okay, we already know what n is. We calculated it from before, so let's go ahead and write down what that is. So n is equal to 2x, 2y, and 1. So now let's go ahead and calculate the curl of f. So the curl of this particular vector field, well, let's go ahead and form our symbolic determinant, I, j, k, ddx, ddy, and ddz. And we have xy, we have yz, and we have xz. When we expand this determinant along the first row, we get the following. We get minus y, minus z, and we get minus x. So this is not a constant vector. Okay, now we're going to form the curl of f of p. We're going to form the composite function. This is the curl of f. We're going to put the parameterization into that. The curl of f of p. Wherever I see y, I put the second coordinate function. Wherever I see z, I put the first coordinate function. Wherever I see x, I put the third coordinate function. Okay. Equals minus y. Okay, let's write down what the parameterization is so we remind ourselves. I'm going to do this one in blue so we have it on the same page. The parameterization of xy is equal to x and y 4 minus x squared minus y squared. So minus y, well, that just stays minus y. Minus z, well, minus z is minus this thing. This is z. So it's going to be x squared plus y squared minus 4. And of course minus x, that stays the same, minus x. This is our curl of f of p. Now we have to form the curl of f of p dotted with n. Well, let's go ahead and remind ourselves what n is. N is equal to 2x, 2y, and 1. So now we're going to take the dot product of this thing and this thing. When we do that, here's what we get. The dot product of this and this is this times that. So it's going to be minus 2xy. And it's going to be plus this times that. So it's going to be I'm going to write it the way I have it here. Minus 8y plus 2x squared y plus 2y cubed, and then plus this times that, minus x. There you go. This is our integrand right here. So now we're ready to solve the integral. And this one I'm going to write out entirely. So the integral over S of the curl of f of p dotted with n dt du is equal to minus 2 to 2 minus radical 4 minus x squared all the way to positive 4 minus x squared minus 2xy minus 8y plus 2x squared y plus 2y cubed minus x dy dx. And when I put that into my mathematical software, I get 0. That's it. In this particular case, this particular vector field is not this vector field. xy, yz, xz, it is not rotating around that surface. It is not circulating around the boundary. That's what this says. Very, very simple. I find n. I have p. I find the curl of f. I form the composite function, curl of f of p. That's a vector. I'm going to dot that vector with vector n. That gives me a scalar. That is this thing. That's my integrand. I take my integrand. I take a look at my domain for my parameter, in this case minus 2 to 2. This is this to this for y, and I solve it, and I get a particular number. That's all that's going on here. In case you lose your way, just work symbolically. As long as you have this, you can just run down the list and find what you need. That's what's important. So I hope you have an opportunity to practice this as much as possible. And again, there is no one thing that you can always do over and over and over again. The process is the same, but the problem is going to come in different ways. Sometimes you're given a parameterization, sometimes you're not. Sometimes it's described one way, sometimes it's described another way. Sometimes you'll have to solve the line integral, sometimes you'll have to solve the surface integral. That's the whole idea. We want to get you to be able to stand back from these problems and think about what's going on. These are reasonably complicated problems because this is serious mathematics. This is not arithmetic here. This is serious mathematics. This is happening on a daily basis. So you should be very, very proud of your ability to actually solve these problems because this is pretty high-end mathematics. Thank you for joining us here at Educator.com. We will see you next time. Bye-bye.